Welcome back. In a previous video, we examined this temperature data, and this was for a beaker of cooling water. And Excel gave us a really good fit here, only we know that that fit doesn't work because according to this equation in here as x, which is time in this example, as time approaches infinity, the temperature of the water would drop down towards 0 degrees centigrade. Not absolute zero, 0 degrees centigrade. This is cooling off below room temperature, and we know that doesn't work. Now, Newton's law of cooling, which is a physics concept that we won't get into, does say that the temperature should drop exponentially. Only in this scenario, the temperature is going to equal some initial temperature times e to the minus, and then there's some constant. I don't know what that constant is, but let's just call it k times t, where t is time and k is just some unknown constant. There's a little bit of a problem here because I know as time goes towards infinity, the temperature should drop down to the room temperature. So what I'm going to do is I'm going to actually add a t sub r to this function where t sub r represents the room temperature. Now, what is this? If I look at this initial equation and I've added this t sub r, this is a vertical shift. So I've taken this function and I have shifted it up by a value of TR, which is the room temperature. And I don't know what that room temperature is, but that should give us a more accurate value for the equation that fits this cooling curve. And just to be complete, let's also take into account a horizontal shift. And that's just a matter of telling me, hey, you might not have started exactly at 0 during this process. And so I'm going to put that horizontal shift in as well. And so this equation will include that horizontal shift. So just a slight alteration here. I'm going to put t minus t0, where t0 represents the horizontal shift. Okay. And then there's this k out front. And then I'll add in the room temperature. So I've got 4 constants I have to work with here. T naught, that's not really the initial temperature. It's the initial temperature value above the room temperature. So the room temperature is also a constant. K is going to tell me how quickly it decays down. And T naught is going to be any kind of a horizontal shift from the 0 point. All right, so what I want to do now is I want to fit all of this into Excel and make it happen. Now, a couple of things I have to keep in mind. Here's a data point right here, and let's just assume that this curve is accurate. There is a value in here from there to there, and that's referred to as the error. You might recall that from a previous video. So this point right here will be not the data point. This point will be the data point. And so that might be, let's just call that t sub I. And this point up here at the top, that will be f of t sub I, where f is this equation right here. Right, so I could use f of time instead of temperature. I'll stick with temperature, but you get the idea. So this upper data point is determined by the equation. The bottom data point, or the bottom point, is determined by the actual data. All right, so let me just repeat that again. The upper point is determined by the time in this function, and the bottom point is actually determined by the data itself. And there's a separation from here to here, and that's referred to as the error. So remember, we're going to examine the error, and then we're going to examine the error squared. All right, so let's do this in Excel and see what we come up with. All right, so this is going to fit the data into some sort of a curve. Now, I need to take into account these constants. So one of those constants is T0, one of them is K, one of them is little t0, and one of them is T room. And for the sake of argument right now, I'm just going to make them all 1. All right, so I'm going to plug the data then, or the time, into this equation up here. So I do this equal sign. I've got the initial temperature, which is right here. So that's cell H2, times an exponential function, which in Excel is exp. And then up in that exponent is k, which is 1, that's cell I2, times, open my parentheses, time, which is this over here, that's cell A3, minus T0, which is over here, that's cell J2, close that parentheses, close the exponential function, and then I'm going to add the room temperature, which is cell K2. And there's my function. And you can see 8104 is nowhere near 94, but that's because these values aren't really 1. All right, then I want to copy that down, but I got to be careful. I want to make sure that H2 is a fixed reference. I want I2 to be a fixed reference. That's all of these guys over here on the right-hand side. And then A3 is going to be a relative reference because as I pull that down, I'm going to want that to stay or change to A4, A5, etc. J2 is a fixed reference. K2 is a fixed reference. All right, so there they are. So I just double-click this right-hand corner, and there are all of the values. You can see that they're huge. Let's go ahead and put some reasonable numbers in here. The room temperature might be around 25 degrees centigrade. T0 will be the temperature above 25, while water boils at 100. That's going to be 75 degrees. And K is almost always something really small. So I'm going to put 3 zeros and a 1 in there for now. And the shift from T0 is probably not very big, so I'll leave that alone. Oh, big mistake in here. I need a minus sign in front of this I. Well, let's just I2. That's the K value, so let's just make that negative, and we should be in good shape. All right, and you can see my temperatures are decaying, not fast enough. By the time I get down to about 25 degrees, my function's only at 84, but that's all right. That's just the fact that my values are not close enough. All right, I want to graph this data, including the third column here. And so I'm going to highlight these 3 columns. I'm not highlighting the top row because I've done that a few times and it's not working. So I'm just going to not do that. Not sure what the deal is there, but let's just pretend it's not going to work. Then I highlight, and there is my data. Right, now the blue is column B. Right, if I touch that, you'll see column A and B show up, and the red is columns A and C. Okay, and what I want to have happen is I'm going to change these numbers in here until the red and the blue line up. Right, so let me just highlight those for now. All right, well, I need a couple of things. First thing, I need my error. Now remember, the error is going to be equal to the function's value minus the data value at that same time. And then I want the error squared, so error squared, so just caret 2. And that's just going to be this number right here squared. And then the other thing I need is the difference or the deviation, and that needs to have the average of the temperatures. So I need to find out what's the average temperature. So let's just put that in here, average temperature, and that's going to be equal sign average, and then all of this good stuff here. So I highlight all those temperatures. Close my parentheses. And we should be all set there. And so the deviation is equal to the temperature minus the average temperature. But that average temperature, we want that to be a fixed value. So I'm going to put a $sign in front of the 5. And then the deviation squared is going to go there. All right, that's just this left-hand cell squared. All right, and then I'll highlight all 4 of those values, double click, and there we go. And then remember R squared was just 1 minus the sum of the squared errors and the sum of the squares. So before I can do R squared, I need the sum of the squared errors, and that's just going to be all of this cell added up. So equal sign, sum, open parentheses, and then add up all of these errors, close that parentheses, right? There's the sum of the squared errors, and then there's the sum of the squared deviations, which remember we used a T on that, so equal sign, sum, add up all of these, close my parentheses, hit the enter key. All right, so the R squared value is equal to 1 minus the sum of the squared errors divided by the sum of the squared deviations. And it's not very good. I want that to be near 1. Really shouldn't even be negative, but that's all right. So let's make this K value even closer to 0. So I'm going to put in another 0 here and then a 1. And when I do that, it's not dropping off fast enough. So I actually did that in the wrong direction. I should eliminate one of the zeros. That gets me back to where I was. Let's eliminate another 0. Okay, and you can see my R squared value is a little bit closer to 1. And also notice over here, the red curve is getting closer to the blue curve. And that's something I really want to have happen. Okay, and so I can keep altering this. Let's knock it down to, let's make it a 2 instead of a 1 there at the last decimal point. That's maybe a little too much. So let's go back to a 1, but maybe put a 5 after that. And that's pretty good. I'm in the 0.97 range there, so I'm kind of liking that. All right, so you can see if I play around with these values for T0 and for T0, for temperature 0, for time 0, and for room temperature, I'll probably be getting closer and closer to where I need to be. I noticed that the red curve is a little higher than the blue curve. Let's knock this room temperature down to 22 degrees. And I got 0.96 there. And maybe declining a little too fast. So let's make the 0014. Then it won't cut down as quickly. And there's, I'm at 0.979. So I'm liking it a little bit more. In a later video, we'll look at this exact same data and I'll show you how to get a really good fit so that this will work really well. But this gives you an idea of how to do a curve fit for data that doesn't fit any of the built-in Excel functions. And that's why we do this manually. Because in engineering, we're going to come across a lot of functions that are not power fits, they're not exponentials, they're not logarithmic, they're not polynomials. And Excel's just not going to do them for us unless we give it some idea on what this temperature or this function is going to be. All right, if you have any questions on this, please leave them in the comments below. Thank you.